Hello friends, in this video we are going to discuss about the N-type substrate MOS capacitor. For N-type substrate MOS capacitor, we will take N-type a N-type substrate. So this is the N-type substrate and this is the silicon dioxide and this is also silicon dioxide and this is the metal layer. So for this, first we will apply a positive potential here and a negative potential here. So we are discussing the accumulation mode of MOS capacitor using N-type substrate. And for that we have applied this type of potential from the outside. So due to this potential, the electric field will be created from positive polarity to the negative polarity in this direction. And due to this electric field created inside the MOS capacitor, the electrons or the majority carriers of the N type will now move towards the interface in the opposite direction to the induced electric field. And due to this movement of majority carriers or the electrons towards the interface, there will be a accumulation of electrons just under the silicon dioxide layer at the interface. So we can say this interface layer is now more N-type than this N-type layer. So this is the accumulation layer or interface layer in the accumulation mode, where a large amount of electrons has been accumulated at the interface layer. So this interface layer will now be more N-type than the other regions of the N-type semiconductor. So we can draw the Venn diagram of this accumulation mode in the following way, and we know that since it is a N-type semiconductor, we can say that if this is the Fermi level of intrinsic semiconductor and if this is the valence band of N-type semiconductor, then this will be the conduction band of the N-type semiconductor. Since it is the N-type semiconductor, so we can say the Fermi level will be near about the conduction band, and this is the Fermi level EFN. So this will be the Fermi level before applying the external potential. Now let us draw the Fermi level that has been changed due to the application of the external potential. So we can draw this like way. So we have applied a negative potential here and we have applied a positive potential here, and due to this application of potential, the previous, let us draw first the previous Venn diagram before the application of the external bias. So there was the EFI just at the middle of the band gap, and there was conduction and valence band in this manner. So this is conduction band, this is valence band of the N type, and since it is a N type material, we can say that the Fermi level of the N type material will be near the conduction band. So this was the band diagram before the application of external voltage in the accumulation mode. Now we have given a positive potential here and negative potential here. So at the interface layer, so this is the interface layer. So at this interface layer, a large amount of electrons will now be accumulated. So we can draw here a large amount of electrons which will be accumulated throughout this interface layer, and hence the band will now modify itself according to this accumulation. So this interface is now more N type than the other regions. That's why the conduction band will now move closer to the EFN. That's why the EFI will also move downwards in this fashion, and the EVN will also bend downwards in this fashion. So this type of band bending will occur during the accumulation mode of N type substrate MOS capacitor. Now we will reverse the voltage direction, that is, if I apply negative potential here and positive potential here, then a electric field will be created in this direction, and due to this electric field, the electrons will move away from the interface in the opposite direction to the induced electric field. That's why some positive donor ions will be left out at the interface. So these are the positive donor ions, and we know that the donor ions are positive ions or positive charges. So due to this accumulation of the donor ions, we can say now the interface will be more positive or more p-type than the other regions. Now if we increase this potential, then the electric field intensity will increase and more number of donor ions will be accumulated in this fashion. That means now this depletion layer width will increase as the intensity of the external voltage is increased. Since due to the application of this type of potential in the MOS capacitor of N type substrate has created a depletion layer. So this mode of operation is called the depletion mode. Now if the voltage or the external voltage is now further increased beyond this depletion mode, then more amount of donor ions will be accumulated near the interface, creating a large charge density, positive charge density near the interface. So let us first draw the depletion mode band diagram of this MOS capacitor. So we can say that here we have given a negative potential and here we have given a positive potential in the depletion mode. So a electric field has been created in this direction. That's why the electrons of the N type are now directed towards the positive polarity, and we know that before applying this positive polarity, the band diagram was like this. This is the EFI and this will be the conduction band and this is the valence band. And since it is a N type semiconductor, then we can say that the Fermi level of this N type will be near the conduction band. So it is EFN. Now we have applied a potential positive here and negative here. That's why the electrons are moving away from the interface, and at the interface positive donor ions has been accumulated. That's why we can say that the conduction band will now move away from the Fermi level of the N type. That's why there will be a bending of the EFI also and bending of the valence band also. So this type of band bending will take place near the interface of the MOS capacitor, and this is the interface or depletion layer. So this is the band diagram of the MOS capacitor of N type substrate in the depletion mode. Now if I increase this potential and this potential, then the electric field potential will increase and the width of the depletion layer, that is XD, will also increase because more number of donor ions will come at the interface, and by increasing the XD will become a maximum value, and that is XDT. So this is the maximum value of the depletion layer. So due to this XDT, now the band will bending in the upward direction by a larger amount. So we can draw the band diagram like this. So previously without bias, this was the EFN and this is the EFI, and EFN will be near the conduction band. So this is the conduction band minima ECN, and this is the valence band maxima, that is EVN. So this is the band diagram before applying the potential. Now we have applied a positive potential here, a very large positive potential, and very negative or very large negative potential here. So, due to this large potential applied, there will be a electric field directed in this direction, which will have a very high value, and due to this a layer will be created, and the value of the width of the layer is xdt. This is the maximum value of the width of the depletion layer, because a large amount of donor ions has been created with a large charge density. So we can say now the band will be bent according to the donor ion concentration. So we can say that this ECN will move away from the EFN, and EVN will move near to the EFN. Similarly, the EFI will move in this direction. So in this way the band will bend according to the donor ion concentration at the interface. Now if we look closely, that the ECN is this amount distance away from the EFN, and EVN is closer to the EFN. That's why we can say that this XDT region is now a p-type material. That means the region near the interface for a large potential voltage has been converted to the p-type material from the n-type material. That's why this layer of depletion charges is called the inversion layer, and the width of the inversion layer is maximum, and the value of the inversion layer width is xdt, and this mode of operation is called the inversion mode. So these are the three modes of operation of a MOS capacitor in n-type substrate. By we can see that there are three modes. First one will be the accumulation mode, second one is the depletion mode, and the inversion mode is the third one. And in the inversion mode, the region near the interface has been converted from the n-type to the p-type substrate. So this is how the MOS capacitor will operate with the applied electric bias from the outside. Thank you.